Welcome to the third of our three-part installment on motor control. This lesson focuses on the control of motor direction. A basic DC motor typically has two leads attached to it, and we apply an input voltage across those two leads. If we apply an input voltage in this direction, we'll get a corresponding current and the motor will rotate in a particular direction. If we flip the polarity of that input voltage, our current will flow in the opposite direction and the motor will rotate in the opposite direction. Thus, by controlling the polarity of the input voltage, we can control the direction in which the motor rotates. Now, physically switching the leads would be rather cumbersome. So one way of tackling this would be to have our motor and attach the motor to the voltage supply via a switch and the other lead to ground via a switch. So in this setup, when both switches are closed, we get our current flow through the motor and thus the motor rotates. We could then set up two additional switches where one switch is attached to the motor potential and the other switch is attached to ground, such that if the first two switches are now open and we close the second two switches, we'll get current flowing in the opposite direction and thus the motor will rotate in the opposite direction. Let's label these switches. This will be switch 1, switch 4, switch 2, and switch 3. So based on the state of the switches, open or close, we can control the direction in which the motor is rotating. So if S1 and S4 are closed while S2 and S3 are open, we'll rotate in the forward direction. And if S2, S3 are closed while S1 and S4 are open, we'll reverse the direction and rotate in the opposite direction. So this configuration allows us to control the direction in which the motor is spinning. And based on the shape, we typically refer to this as an H-bridge circuit. An H-bridge is typically what's used to control a motor because not only does it allow us to control the direction of the motor, if we replace the switches with transistors, we can also control the speed of the motor. Here's an H-bridge circuit using MOSFETs instead of mechanical switches. The bottom half of this H-bridge circuit has two NMOS transistors. Let's take a look at this node here, and let's resketch this transistor up top over here. If this switch is closed, then this voltage is going to be equal to effectively V motor. This transistor has a V gate as well as some threshold voltage. And in the case where we made this an NMOS transistor, we'd need this gate voltage to be greater than the summation of the motor voltage, or the source voltage, plus the threshold voltage. If this is the case, then this is going to require a large gate voltage, and it may be difficult to provide this using something like an Arduino. In contrast now, if we make this a PMOS transistor, then the gate voltage now must be less than V motor minus the threshold voltage. So in this setup, we could turn the transistor off by applying a gate voltage close to V motor. And then we could turn the transistor on by applying something like ground. So as a result, the H-bridge circuit will have two PMOS transistors up top. Using this setup, if we apply voltages such that this PMOS transistor is on and this NMOS transistor is on, and this PMOS is turned off as well as this NMOS transistor is turned off, then the resulting current path through the motor will look like this. And thus the motor will now spin in the corresponding direction. Alternatively, if we turn this PMOS off as well as this NMOS off, then turn this NMOS on and this PMOS on, now the resulting current flows in this direction. And thus now we can turn the motor in the opposite direction. Now, given this H-bridge circuit, it's also important to consider the integration of flyback diodes for each transistor. Just be aware, though, that when using MOSFETs for an H-bridge, often the flyback diodes are actually built into the transistor itself. In the case where we're using BJT transistors for our H-bridge circuit, then we're definitely going to want to include flyback diodes at each transistor. So let's take a look now at one half of the H-bridge, often referred to as a half-bridge circuit. Analyzing the half-bridge circuit will help us better understand how we can apply voltages to these transistors and control both the speed and direction of the motor. Let's consider here a V motor of 6 volts, and we'll connect the gates of the NMOS and PMOS transistors together. Let's begin this analysis by applying 0 volts to the transistor gates. Recall that for an NMOS transistor to turn on, the gate voltage must be greater than the source voltage plus the threshold voltage. While for the PMOS transistor to turn on, that gate voltage must be less than the source voltage minus the threshold voltage. If we assign threshold voltages to each of these MOSFET transistors of 3 volts, then we see that for the NMOS transistor, 0 volts is not going to be greater than 0 volts, since the source is tied to ground, plus the threshold voltage, and thus this transistor is in the off state. For the PMOS transistor, we need the gate voltage to be less than the source voltage, in this case 6 volts, minus the threshold voltage. So we need the gate voltage to be less than 3 volts, 6 minus 3. Since the gate voltage applied here is 0 volts, the PMOS transistor is in the on state and current is allowed to flow in this direction. Let's now apply 5 volts to this half-bridge circuit using something like our Arduino. In this case, the 5 volts applied to the gate of the PMOS transistor is not going to be less than the 6 volt source minus the 3 volt threshold, and thus this PMOS transistor is now in the off state. The NMOS transistor, however, that gate voltage of 5 volts is now greater than the source volts, in this case ground, plus the 3 volt threshold. So this NMOS transistor is now in the on state, and current is now allowed to flow through the motor in this direction. Let's take a look now at a relatively straightforward way to control both speed and direction of a motor. If we want the motor to rotate in one direction, we could set one input equal to ground, set it to 0 volts, and define a PWM input on the other side of the HBridge. Whenever this PWM signal is high, we'll have this transistor on, this transistor off, and this transistor on, and as a result, current will flow through the motor in this direction. When the signal is low, the states of these transistors is reversed, so this PMOS will be on, and this NMOS will be off, and thus there's no real current path through the motor. To spin the motor in the opposite direction and still maintain the control of speed, we can now connect the left side of the HBridge to ground and the right side input to the pulse width modulated voltage. If this is the case, we now have this NMOS is off while this PMOS is on, this NMOS is on while this PMOS is off, and the current is now permitted to flow through the motor in this direction. So now we can control the speed of the motor in the opposite direction using this PWM signal at right. HBridge circuits are widely used in a variety of mechatronic systems, so it's relatively easy to get your hands on a COTS or commercial off-the-shelf HBridge package. For example, this is the TI SN754410, and this is a very common package, typically limited to about an amp of current. So based on the torque that you need for your motor, that'll drive the requirement for amperage, and this package may or may not be suitable for your needs. Another example of a commercially available HBridge is the ST-L298. And there's also a variety of motor shields available for using these HBridges with something like your Arduino.